Okay, next we're going to talk about data management and manipulation. And this is in the module for data management, visualization, and reproducibility. And we're going to start with our first lecture on data management, or keeping all of your files and folders organized in a way that allows you to work cleanly with your data. So no required readings for class today. There are a few optional ones. The Lind paper from 2016 we'll talk about later in the lecture, and it's a really nice example of how you can build relational data sets for large data sets. And this could be useful if you want more information beyond what we talk about. And then another 10 Simple Rules paper from Hart et al. In 2016 if you're looking for more info on digital data storage. And then a nice paper by Boer et al. From 2009 that talk about some simple guidelines for effective data management. It's a little older, but it still has a lot of really useful information. So why do we want to manage our data? It allows you to quality control your data more easily when you can see everything and you know where things are located, etc. It helps you stay organized through the whole process of file management, script creation, version control, backups, etc. If you know where everything is and they all live in folders that are clearly marked, it'll make your life so much easier. And this enables reproducibility. So this helps us keep our data fair. You always want to be able to recreate anything you've done, figures, analysis, etc., from the data that produced them, even 3 years later. And it helps you share your data more easily for future meta-analyses. Again, this is part of the FAIR guidelines, and this really helps you keep your work in the bigger picture and helps move your field forward if your data can be used for meta-analyses in the future. But before we can even get to R, we need to think about organization and how that really is the key to our projects and data management. So for each R project or manuscript, you're going to want to have a set of folders. So I don't know if you're like me, but in the past, I used to have every single data file, figure, etc., all in one giant folder. And that just created chaos when I was trying to reproduce things because there were just too many files and I couldn't find things. So I've recently moved to a system where I have a set of folders nested within each project folder. And so here are some suggestions of the folders you could have within each project. But of course, there are many options and it's going to depend on the kind of work you're doing. So you could have a data folder, a data wrangling folder, analysis, graphics, documents, README, etc. And I'll describe them next. So here's some more detail, right? So in your data folder, you could have your raw data, which is read-only, pristine backup, not to be touched. Likely this is in Excel, because that's probably how it was entered. And then you could have your tidy data, which is another file. We're going to talk about how to tidy your data in a little bit. And this is sort of an intermediate between your raw data and before you get to your data analysis. Then you can have a data wrangling folder where you have a script that compiles all your data sets. They clean them, transform them if necessary, and put them into a single usable data set. Then you could have a folder for your analysis and your figures, maybe a documents folder that also houses a manuscript folder where you put all of your drafts of your manuscript, and a literature folder, and then also a README folder that contains your metadata, which we've talked about is really important to keep track of, and then also a place to write down the driving questions and purpose of the project or other notes for the future. There's nothing like being in the middle of a project and just, being in the weeds of everything and sort of forgetting why you're doing what you're doing. And so if you have your driving questions and purpose written down in a succinct couple of sentences, it can be really helpful to go back to that and remind yourself of why you're doing your project. And so we'll talk about this throughout the course, but your code will stay cleaner if you use many smaller scripts. So for example, one for all your analyses or one for all your figures, or my personal preference is to have one for each analysis and the associated figure, so you can always keep everything together. And so I'll have multiple sets of those for each project. So some tips for entering your raw data before we get to our analysis. So when you're entering your data, you want to try to have no spaces in your column headers. You want to note all units in either the headers or in associated metadata. This is often easier to do in the metadata. And remember, R is case sensitive, so you want to keep your column headers in a case structure, like we talked about last time, so either snake case or dot case, etc. And don't forget there's a difference between 0, NA, and a blank cell. And they all tell you something different. And so often, if you have someone helping you enter data, they may not think about this. But a 0 could mean the value is 0, or sometimes people write 0 to indicate that you don't have data for that row. And you really want to watch that, right? You want that to either be, preferably you want that to be NA, but I suppose it could also be a blank cell. And then you want to fill all columns. So on the left, you can see that the plot and species information is not filled for all rows. And so what you want to shoot for is something like on the right, where you have every single row filled for every single column. And so a little bit about relational data, something to think about when you're thinking about how you enter your data. So you want to store your data as smaller units, as I was saying, and you want to do this in a hierarchical way and by type. And you want to be able to link them then through code. So for example, you may store your site level data in one file and then your plot level data in another. And then you link these data sets through code in a relational way. And this helps avoid confusion and repetition, and it's also great for large interconnected data sets, especially those that can change frequently. So data management systems play well with data that's in this format, for example, Tidy or SQL. And these data sets can then be linked in a one-to-one, many-to-one, or one-to-many way. And so here's an extreme example of relational data, but I just wanted to give you all an idea of what that looks like. This is from the Lind paper in 2016, and this is a representation of the data from the Nutrient Network. You can look that up if you're interested. So here you can see that, for example, there's site data, right? So each site has a set of data. There's site data that comes from the climate, weather, nitrogen deposition, etc. And those all link through either one-to-one or n-to-one to site level information. So all of the important things about each site, to plot level information, etc. And then those data sets can also link to observations. So this is the data you collect. For example, your soil characteristics or biomass that's collected every year or plant cover that's collected every year. And so you can see this is a very powerful technique for working with really large data sets. And if you're interested, check out the paper. And one thing that can be really helpful for this is Git and GitHub. So GitHub is a really great resource for managing your data and code. And if you're interested, there are lots of great resources out there. So here's a few, but there are a lot of really great resources out there. So please complete quiz 2.1 on Canvas and continue on to the next lecture.